Carl Schwarzschild solved Einstein's field equations by hand in a dugout on the Russian front in the winter of 1915. A matter of weeks after Einstein published them, faster than Einstein himself thought anyone could manage it. 4 months later, Schwarzschild was dead, killed by an autoimmune disease he picked up in the trenches, and he never lived to see what his own mathematics actually predicted. In 1939, Einstein published a paper arguing that the very object his own theory demanded, a black hole, could not really form in nature. He thought it was too extreme, a mathematical ghost, not a real place. In 2019, we photographed one anyway, and in 2022, we photographed the one sitting 27,000 light years from where you're sitting right now, at the center of our own galaxy. In 2015, 2 black holes collided 1 billion light years away, and for 0.2 of a second, that collision radiated 50 times more power than every star in the visible universe combined. We have weighed black holes, photographed them, listened to them crash together across the universe. And after all of that, most people who follow science closely still believe the single most basic thing about a black hole is wrong. They believe it's a hole, something you could fall into, and in principle, come out the other side of, somewhere else. That belief isn't ignorant. It isn't uneducated. It's the exact spot where an otherwise very good physical intuition is missing one gear, and I want to show you which one. Here's the shape of the idea, in the words most people actually use for it, because getting the shape right matters before we take it apart. A black hole is a hole in space. A hole has 2 sides, the way a hole in a fence does. You go in one side, and if you don't hit anything solid, if your ship is fast enough, strong enough, you come out somewhere else. Maybe another part of the universe. Maybe another universe entirely. It isn't a crazy idea. It has real physics attached to it. Actual working solutions of Einstein's equations. That's exactly what makes it dangerous. This isn't like believing the sun is a ball of burning coal. That's just wrong, full stop. This is like believing that because a bridge exists on a map, you can walk across it. The map is accurate. The bridge is real. What's missing is one detail about the bridge that the map doesn't show you, and that detail is the entire ballgame. Start with the simplest black hole in the mathematics, the one that doesn't spin, doesn't carry charge, just mass sitting there, warping the space around it according to the same field equations that govern every gravitational effect we've ever measured. Cross its horizon, and something happens to you that has nothing to do with speed or armor plating or how brave you are. Outside the horizon, the crushing center is a place. It's somewhere in space, and like anywhere in space, you can choose not to go there. Inside the horizon, that center stops being a place and becomes a moment in time. Every direction you can travel, every pathlight itself is permitted to take points toward it. The same way every direction you can travel through Tuesday points toward Wednesday. You cannot avoid Wednesday by steering around it. Once you're inside a real black hole's horizon, you cannot avoid the singularity by steering either, because steering is a spatial idea, and the singularity has stopped being a spatial problem. This is the first gear that breaks in the backdoor myth. It isn't that the exit is guarded. It's that inside a real black hole, there is no longer a direction called toward the exit. There is only a direction called later. Now here's where it gets genuinely interesting, because the bridge on the map isn't a metaphor. It's a literal object sitting inside Einstein's own equations. In 1935, working with a young physicist named Nathan Rosen, Einstein looked at the fully extended version of that same simple black hole solution and found that it doesn't just connect a region of space to a crushing point. It connects 2 separate, distant regions of space to each other, joined at a shared throat, like 2 funnels welded together at their narrow ends. That object has a name, the Einstein-Rosen bridge. It is real mathematics, done by the man who invented the theory, published in a real physics journal. If you stopped reading right there, You'd walk away thinking you'd found the loophole. A real, Einstein-certified tunnel between two places. This is exactly where the myth gets its power, because everything up to this sentence is true. And this is exactly where I have to tell you the detail the map leaves out. The detail that turns a genuinely real bridge into a bridge you can never, under any circumstances, actually use. The detail is timing, and once you see it, you cannot unsee it. The Einstein-Rosen bridge isn't a static tunnel sitting there waiting for you, the way an ordinary bridge sits over an ordinary river whether or not anyone crosses it. It's dynamic. The throat opens, and then it closes, and the closing is not slow. Plot it out on the kind of space-time diagram physicists actually use for this, and you'll find two funnels flaring apart, connected for one brief instant, and the throat pinches shut faster than anything obeying the universe's speed limit could possibly cross from one side to the other. Not because someone built an extremely fast door, because the geometry itself is collapsing at a rate that outruns light. You would need to travel faster than light to make it across before the bridge stopped existing, and the moment survival requires breaking the speed limit, you've left the territory of difficult engineering problem and entered the territory of this was never a door, it was a mathematical event that briefly resembled one. That's gear number 2. The very first wormhole anyone ever found, sitting in Einstein's own theory, fails not because it's guarded and not because it's far away. It fails because it doesn't stay open long enough to have ever been a bridge for anyone. I spent years at the lab bench before I spent decades at the typewriter. And the first hard lesson biochemistry teaches you is that having the right molecule is not the same as having a molecule that works. I once spent most of a summer purifying an enzyme that had, on paper, every feature it needed. The right active site, the right cofactor, the right fit for its substrate. And it did nothing, because the temperature in that particular assay denatured it in the 11 seconds between mixing and measuring. The enzyme wasn't wrong. My understanding of when it existed as a functional object was wrong. That's precisely the trap with the Einstein-Rosen bridge, and it's a trap that's going to show up 2 more times before this video ends, so hold on to it. Something can be completely, rigorously real in the mathematics and still be functionally unavailable to you. Not because it's fake, but because it doesn't exist for long enough, at the right moment, under the right conditions, for you to use it. Physicists rarely get fooled by this. The rest of us get fooled by it constantly, because we're used to things that are real also being things we can reach. There's a version of this that gets even more tempting, because real black holes, the ones that actually form from a collapsing star, spin. And a spinning black hole doesn't crush you into a single point the way the simple, non-spinning solution does. In 1963, a New Zealand mathematician named Roy Kerr solved Einstein's equations for a rotating mass, and the object he found has a singularity shaped not like a point, but like a ring. Fall into a spinning black hole along the right trajectory, and the idealized mathematics of the Kerr solution says you can, in principle, avoid the ring entirely and pass through its center, out the other side, into a region the equations describe as a separate, distinct patch of space-time, connected to ours, but not part of it. Some versions of that idealized solution even permit paths that loop back on themselves in time. This is the object popular explainers reach for when they want to sound rigorous about time machines, and for good reason. Unlike Einstein and Rosen's bridge, nothing forces this one to pinch shut. It genuinely doesn't collapse the way the non-spinning version does. So why can't you use it? Because the Kerr solution, in its full, perfectly symmetric, eternally existing form, describes a black hole that has always existed and always will, alone and undisturbed, forever. And no black hole in this universe has ever matched that description, because every real black hole formed from something, at some point, out of collapsing matter, and every real black hole afterward keeps absorbing the ordinary debris of being a black hole. Gas, dust, starlight, its own earlier radiation, falling in behind whatever else arrives. In 1990, physicists Eric Poisson and Werner Israel worked out what happens to that inner boundary, the one you'd need to cross to reach the other side. Once you stop pretending the black hole is perfectly isolated and add back even a trace of realistic infalling material, the boundary doesn't stay open and gentle. It amplifies whatever falls toward it without limit, a runaway effect now called mass inflation. And the smooth inner horizon of the textbook solution turns into a genuine curvature singularity of its own, one that would destroy anything crossing it, using nothing more exotic than the ordinary, everyday matter that any real black hole is constantly swallowing. The friendlier door was never a door either. It was the same trap as Einstein's bridge, wearing a disguise good enough to fool the idealized mathematics and bad enough to fail the instant you added back the universe's ordinary mess. So if neither the simple bridge nor the spinning one survives contact with a real, messy universe, is there any way, even in principle, to prop a wormhole throat open on purpose? There's exactly one, and the story of how physicists found it is one of the stranger collaborations in the history of the field. In the early 1980s, Carl Sagan was writing a novel about a scientist who receives instructions from an alien civilization to build a machine that carries her across the galaxy, and he wanted the physics in that novel to actually hold up rather than just sound impressive. So he asked a friend of his, the physicist Kip Thorne, whether his character could survive a trip through a black hole. Thorne ran the numbers and told him no. A black hole kills her. No version of the physics allows otherwise. But there might be another way, if Sagan was willing to ask for something almost as strange as faster-than-light travel. That question, asked because a novelist refused to let bad physics slide, sent Thorne and his student Michael Morris down a path that produced one of the most cited technical papers in the field 3 years later, in 1988. I never met either of them, but I understand exactly what Sagan was asking for, because I've spent my own career refusing to let a good story get away with physics, I don't believe. What Thorne and Morris found is called a traversable wormhole, and the traversable part is the entire point. Unlike Einstein and Rosen's bridge, this one is built to stay open long enough for someone to walk through it in both directions and come back to tell you about it. But the price for that stability is severe. Ordinary matter, every kind of matter we have ever directly measured, gravitates the way you'd expect. It pulls things together, curves space-time inward, and left alone, that inward curve is exactly what pinches a wormhole throat shut, the same way it pinched Einstein's bridge shut. To keep the throat open, you need something that does the opposite, matter with negative energy density, something that pushes space-time outward rather than pulling it in, propping the throat the way a strut holds up a collapsing tent. This isn't exotic in the sense of a rare element that's hard to synthesize. It's exotic in the sense that nothing in the ordinary matter budget of the universe behaves this way, ever, under any conditions we've cataloged. And here's the part most explainers skip past too quickly to matter. Negative energy density is not science fiction. It's real. We've measured it in a laboratory. It's just almost unbelievably small. And that gap between real and usable is where the entire dream quietly goes to die. The measurement is called the Casimir effect, and the experiment is almost absurdly simple to describe. Take two uncharged metal plates, place them a few hundred nanometers apart in a vacuum, and they pull toward each other. Not from any charge or ordinary force, but because the plates restrict which quantum vacuum fluctuations are allowed to exist in the gap between them, and that restriction shows up as a tiny, measurable negative energy density right there in the gap. It was predicted in 1948, measured with real precision in the 1990s, and it is completely uncontroversial physics. So the belief that feels reasonable at this point is, fine, if we can produce negative energy density in a lab with two metal plates, then a sufficiently advanced civilization could surely produce enough of it, sustained for long enough, to hold a wormhole throat open. This is where the second wall shows up. And it isn't a technology wall, it's a law. In the 1990s, Physicists Larry Ford and Thomas Roman worked out what are now called quantum inequalities, and what those inequalities say, in plain terms, is that there is a hard trade-off in quantum field theory between how negative an energy density is allowed to get and how long it's allowed to stay that negative. You can borrow a large violation for an extremely short time, or a tiny violation for a longer time, but you cannot borrow a large violation for a long time. Not with better engineering. Not ever, under any theory of quantum fields we currently trust. Run the numbers for a wormhole throat large enough for a person, held open long enough for a person to actually walk through it. Not a science-fictional starship, just one human being, walking at a human pace. And the quantum inequalities say the exotic matter needed has to violate the ordinary energy conditions by a density and duration that's off by dozens of orders of magnitude from anything the Casimir effect or any known quantum process has ever produced. Not twice as much. Not 1,000 times as much. If the exotic matter in a real Casimir effect experiment were the width of a single atom, what you'd need for a walkable wormhole throat would stretch past the edge of the observable universe. This is the enzyme problem again, the one from the top of this video, in a bigger and colder form. The substance is completely real, and it is still functionally unavailable, and no amount of wanting it to be otherwise changes the assay. That gap isn't an engineering problem you close with better funding, or a bigger particle accelerator, or 3 more centuries of technology. It's a gap that tells you something has gone wrong with the premise, not the plan, and the premise. That the only thing standing between us and a black hole's back door is our current level of technology, is the actual lie inside the backdoor myth. Now you can see exactly where it hides. I had an editor for 2 decades who used to slide my manuscripts back across his desk with a single word scrawled in the margin: mechanism. Not boring, not wrong. Mechanism. He wanted to know, every single time, exactly how a thing worked, gear by gear. And if I couldn't answer that, he didn't care how good the sentence was. I hated him for it for about the first 3 years, and then I understood he was doing me an enormous favor, because mechanism is the only question that reliably separates an idea that's merely appealing from an idea that's actually true. The backdoor myth is appealing. It's been appealing for longer than Einstein and Rosen have been dead because it answers a very old human wish, that anywhere impossibly far away might secretly be impossibly close, if you can just find the right doorway. Every culture that has ever told stories about distant, wonderful places has also told stories about shortcuts to reach them. What I'm doing to you right now in this video is exactly what that editor did to me for 20 years. Asking you to set the appealing version aside and ask, gear by gear, does this actually work? And we are not done asking that question, because we haven't reached the strangest part yet. Here's the strangest part, and it's the part that gets tangled up with everything I've just told you in almost every popular explanation of black holes you've ever watched. Time dilation is completely real, rigorously measured, and has nothing to do with the backdoor myth at all. And conflating the two is exactly what keeps the myth alive. Time dilation says clocks run at different rates depending on how fast they move and how deep they sit in a gravitational well, and we've verified this so many times, in so many independent ways, that it's now baked into consumer electronics in your pocket. The GPS satellites orbiting above you right now run about 45 microseconds a day faster than clocks on the ground, purely from sitting higher in Earth's gravity well, and about 7 microseconds a day slower, purely from moving fast enough to feel a mild version of the same effect Einstein described for objects near light speed. Net result: satellite clocks gain about 38 microseconds every single day compared with a clock in your hand. That sounds small enough to ignore. It isn't. Left uncorrected, that daily drift would put your GPS position wrong by roughly 10 kilometers within 24 hours, and further off with every day that follows, enough to put your blue dot in the wrong neighborhood by the end of a week. This isn't new physics, either. In 1959, Two physicists at Harvard, Robert Pound and Glenn Rebka, measured this same gravitational effect over a tower 22.5 meters tall, the height of a modest apartment building. Using gamma rays and an effect sensitive enough to detect a frequency shift of about 2.5 parts in a quadrillion, and they confirmed Einstein's prediction to within about 10% using nothing but a physics building on a college campus. A few years later, refinements to the same setup pushed that precision down to about 1%. Near a black hole, that same effect doesn't shift you by microseconds. It can shift you by years. Kip Thorne, the same physicist Carl Sagan called about the wormhole, later worked out, for the film Interstellar, what it would actually look like to orbit close to a massive, rapidly spinning black hole. 1 hour on a planet in that orbit for every 7 years passing for anyone who stayed farther out. That number isn't a screenwriter's invention. It comes out of solving the actual equations for a real, if extreme, orbit. And here's exactly where I need you to slow down and separate two things that every documentary you've ever watched has smeared together into one vague impression of black hole weirdness. Time dilation lets you travel forward into the future of the rest of the universe by aging slowly relative to it. It does not, in any sense, let you travel sideways into a different place. Those are not two versions of the same trick. They are not even the same category of trick. I want to tell you something that has bothered me for longer than I'm comfortable admitting on camera, because it sits underneath everything I've told you so far, and I don't have a clean way to close it off. If a black hole can form, and if, as Stephen Hawking showed in 1974, black holes very slowly radiate energy away and eventually evaporate completely. For a black hole the mass of our Sun, that process takes something on the order of 10 to the 67th years. A number so large that the current age of the universe is a rounding error against it, but the mathematics says it happens eventually. Then everything that ever fell into that black hole, every last bit of information about every particle, every structure, has to end up somewhere once the black hole is gone. Quantum mechanics is built on a principle called unitarity, which says, in essence, that information is never truly destroyed, only scrambled. And in principle, you could always reconstruct the past if you tracked every detail closely enough. General relativity, meanwhile, describes a singularity that looks, for all the world, like a place where information simply stops existing. Those two pictures cannot both be fully true as we currently understand them, and for most of my career I assumed this was a problem someone else would eventually solve, a loose thread in an otherwise finished sweater. It isn't a loose thread. It might be load-bearing. In 2012, a group of physicists pointed out that if you try to preserve both unitarity and the smooth, gentle experience relativity promises anyone crossing a black hole's horizon, you run into a contradiction sharp enough that one side has to give. And the proposal that came out of that argument was almost violent. Maybe the horizon isn't gentle at all. Maybe it's a wall of high-energy radiation. A firewall that would incinerate you the instant you touched it, which would mean one of relativity's most basic promises. That falling through a horizon should feel like nothing special, because nothing special happens locally, might simply be wrong for the horizons of old black holes. That paper started a fight inside theoretical physics that, as of my writing this, still isn't fully settled. But the strangest response to that fight didn't come from resolving the paradox. It came from a paper by Juan Maldacena and Leonard Susskind in 2013 that proposed something genuinely bizarre, that an Einstein-Rosen bridge, the same collapsing, unusable wormhole I described to you earlier in this video, might be mathematically identical, not merely similar, identical, to a pair of quantum-entangled particles. Two particles correlated across any distance, and a wormhole connecting 2 points in space-time treated as two names for exactly the same underlying object. They called it equals Epper. This bothers me for a personal reason too, not only a professional one. Decades ago, I built an entire series of novels around the premise that a civilization, given enough information and the right mathematics, could predict the large-scale future of an empire of 100 billion people, the same way you can predict the pressure of a gas without tracking every molecule inside it. I believed, and I think I still believe, that this is the correct spirit of physical law. Information isn't lost, it's only distributed, and given enough of it, prediction is possible in principle even when it's impossible in practice. A black hole that genuinely destroys information isn't just a technical inconvenience to that worldview. It's a hole in the floor underneath it. If there is even one place in this universe where information can truly, permanently vanish rather than merely become unreadable, then the deepest assumption behind everything I've ever written about a knowable, lawful universe has an asterisk on it I cannot currently remove. Most physicists I respect think unitarity wins in the end, that the information gets out, encoded somewhere in the radiation, in ways we don't yet know how to read. I think they're probably right. But probably is a word I don't enjoy using about the foundations of reality, and I would be lying to you if I pretended otherwise. So let's bring this all the way back to where we started, because this is where the last gear falls into place. If equals Epper is even approximately on the right track, and more than a decade of theoretical work has taken it seriously enough that it's no longer treated as a curiosity, though it's nowhere near settled, then wormholes aren't rare, exotic objects that might exist somewhere out past the edge of engineering possibility. They might be the default relationship between any two particles that have ever interacted and become entangled, which, traced back far enough through the history of the universe, could mean an almost unimaginable number of them, threaded invisibly through empty space, right now, around you, in this room. And you still cannot fly a ship through a single one of them, not because they're too small, and not because you lack the exotic matter, though you'd need that too. It's because what a wormhole connects, in this picture, isn't two locations the way a tunnel connects two ends of a mountain. It connects two correlations. There's no throat with a measurable diameter. There's no direction called through. The thing you pictured, a door, a hallway, a place you enter and a different place you exit, was never the right shape for what's actually being described at any point in this story, from Einstein's bridge to a Casimir plate to a pair of entangled electrons on opposite sides of the galaxy. That's the enzyme problem a third time, in its final and strangest form. The object is real, the mathematics is rigorous, and it is still not available to you in the shape you wanted it in, because you were never using the right container to hold the question. Here's the actual size of the question you walked in with, even though you didn't know it at the time. You came here asking whether you could travel through a wormhole, which sounds like a question about vehicles and thresholds and exotic fuel. But every path through this video has pointed at the same, much larger fact. Distance itself might not be a fundamental feature of reality. It might be something that emerges, the way temperature emerges from the average motion of billions of molecules, even though no single molecule has a temperature of its own. If two particles a billion light-years apart can be connected by the same mathematics that describes a wormhole, then a billion light-years apart might be a description of how little they're entangled, rather than a fact about the empty space sitting between two fixed points. Space, in that picture, isn't a stage that things happen inside of. It's closer to a pattern that things happening leave behind, the way a traffic jam is a real, measurable thing that isn't made of any substance called jam. It's made of cars and their relationships to each other, and it can evaporate completely the instant those relationships change, without a single car being destroyed. You didn't come here to ask whether wormholes are physically buildable. You came here to ask, without knowing you were asking it, whether the space between you and everything you love is a wall or a symptom. I have been publicly, professionally wrong about the universe more times than I can comfortably count, and every single time it has felt exactly the same. Not like falling, but like a floor I didn't know I was standing on, turning out to be a trapdoor. I was wrong about how quickly this field would settle its argument over singularities. I was wrong, for a good while, about how seriously to take the idea that entanglement might sit underneath distance rather than the other way around. I expect to be